more probability. We're just talking about what happens if I have independent events, but now we'll ask, how would I know if they're independent? How do I figure that out? We'll talk about a joint distribution. We keep it simple for now, just two events, X outcomes in the columns, Y outcomes in the rows. Want to know what's the probability of these outcomes. If these are independent, we did it before, then the probability of X occurring is unaffected by Y. So knowing the probability of Y is irrelevant. It doesn't tell me anything about the outcome of X. In our notation, that vertical line there means given. So we read that probability of A given B is equal to just the probability of A. Now, if we're talking about sports teams, then although you might have trouble convincing a fan about this, the probability of their favorite sports team winning is probably irrelevant to their choice about wearing the sports jersey. You may not be able to persuade everybody in that. That's partly why statisticians have a reputation of being no fun. But setting aside the emotional impact or the fun, these are independent events. One is irrelevant to the other. Now, maybe if you're talking about really small kids playing a game, then maybe the probability of a parent being there, cheering for the kid, perhaps it's not irrelevant. But to begin, I'll assume these are independent. So here, X takes the value 1 with 60% probability, and X takes the value 2 with 40% probability. Y takes the value of 1, 2, or 3 with probabilities 50%, 30%, 20%. Assuming independence, probability of each of those particular cells is the multiplication. Probability of getting, say, X equals 2, Y equals 3 is going to be 8%, because that's 40% times 20%. But how would we distinguish these from another case that's not independent? Label those outcomes as A and B. Now A here can take the value of 1 or 2, while B can take the values of 1, 2, or 3. What is now the probability of A equals 2, B equals 3? The table shows the probability is 0.1, 10%. But how would I distinguish that from previous? One way is to look at the marginal probabilities. The marginal probabilities are calculated by writing in the margins. Thus the name. Real creative, I know. Add the probabilities in the rows or the columns and write the sum in the margin. That's why they're called the marginal probabilities. That's where you write them, that's what they're called. On the left-hand side, I have the XY example. On the right-hand side, I have the AB example. The XY example is independent, while the AB example is not independent. To see that, calculate the marginals. Add up the probabilities horizontally. So if Y equals 1, then X equals 1 with probability of 30%, or X equals 2 with probability of 20%, so the sum is 50%. Do that again for those of the other horizontal sums. You do the vertical sums as well. X equals 1, then Y can take any of 3 values, add up those values to get 60%. If X equals 2, the sum is 40%. Move to the right-hand side with AB, can calculate the marginal values. So the row sums are 38, 35, and 27%, while column sums are 65, 35. Let's talk about how to interpret those so you can understand what independence means. Probability of A equaling 1 is in total 65%, because there are 3 different ways or 3 different places where A equals 1. So what is the probability of getting A equals 1 along with any value of B? Just add up the probabilities. Note the probability of A equals 2 is 35%, which checks out, says those got to equal 1, or sum to 1. Always good to check your math. If they do not add up to 1, then that'd be some mistake, because this is supposed to be an exhaustive list of all the possible things that could happen. Going back to our games analogy from the previous time, we said we're going to assume there's no such thing as a tie game, because that just keeps it simple. If there are tie games, then we'd have another column. If these marginal probabilities do not each add up to 1, then that's a flag something went wrong in the little model. Finally, note for the XY model on the left, the probability in the center boxes is equal to the probability of the 2 marginals. For instance, the product of the 2 marginals. For instance, the probability of X equals 2, Y equals 1, that's 0.4 times 0.5, which equals 0.2. That's because X and Y are independent. But that's not the case in the AB table there. The next step, once we've calculated our marginal probabilities, is we can find the conditional probabilities. To find the conditional probabilities, we divide each value of the joint distribution by the marginal. Suppose we want to find the conditional distribution of the values of b conditional on a being equal to 1. There's a 65% chance of a equals 1, so the probability of b equals 1, given that a equals 1, is calculated as 25% divided by 65, which is the 0.03846. Probability of b equals 2, given that a equals 1, was 0.23. Divide 23 by 65, that's 0.3538. The joint probability, a equals 1, b equals 3, 17%. Divide by that by 65, get 26.15. We just work through and calculate all these probabilities. Can do the same thing conditional on a equals 2. What are the probabilities of different outcomes of b? Just do those simple calculations. Note, these are different numbers. They're not equal to marginals. They're not equal to each other. They're not independent events. Note the little bit of algebraic notation. We use that vertical bar to mean given that. What is probability of b given that a equals 1? If we're to do the conditional probabilities for the xy table, you'd find those conditionals are all equal to the marginals. It's a rather boring bit of arithmetic, so I'm not going to lead you through that, but you can confirm on your own. Let's do something a little more interesting with the BRFSS data. We've got information on each person's health insurance, which are the columns here, and then whether they've ever been diagnosed with depressive disorder as rows. We can ask, sorry, I just did the opposite, rows and columns, but you got it there. We can ask, are these statistically independent? Which is equivalent to asking, are these uncorrelated? Now, you're probably answering something like, duh, but this is an example of how we think like a statistician. First step is to get the probabilities. So divide the number of observations in each box by the total number of people in the sample. That's the top version of the table. Next, calculate the marginals, adding up the probabilities by rows and by columns. Then calculate conditional probabilities, either looking at rows or columns. The way to read this is, for instance, let's look at the table where we're divided by columns. So it's conditional on somebody's mental health diagnosis. Each column there adds to 1. Conditional on a person having had a depressive diagnosis. 41.8% had private insurance, 28.9% had Medicare, 12% had Medicaid, 12.3% had other government insurance, and 5% were uninsured. Compare with those who did not have that diagnosis. 47.7% had private insurance, 32.6% had Medicare, lower levels of other government programs, and 5.5% uninsured. We can see some differences. The other way of looking at it, divided by the rows, asks the question, conditional on a certain insurance status, what are the proportion who did or did not have that diagnosis? Among those with private insurance, 81.3% had never been diagnosed, while 18.7% had. That's not far different from those without insurance, but it's quite different for those with Medicaid. Almost 37% had. Although it's often tempting, let me caution against stating that any of these show causation. It's not true here, not in general. Likely the case here that causality goes in both directions. Someone with a history of mental health issues might be more likely to be on Medicaid, but someone without insurance might be less likely to be diagnosed. So there's causality in both directions. Finish up with some of the equations of what we're doing here, showing the general case. Probability of A, given that B happens, that's probability of A and B both happening, divided by the probability of B happening. That's how we define conditional probability. We can swap A and B. Probability of B given A is probability of A and B combined happening, divided by probability of A. Put together those two equations on the top, do a little bit of substitution, bit of algebra, and get what's known as Bayes' theorem. Probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. We'll come back to some of the ways in which that's useful for understanding the world, but now it just comes right out of the definitions.